Alkene undergoes addition reactions. Addition reaction is opposite of elimination. You start with an alkene and you react with an alkene with a reagent that has part of it an electrophile and part of it a nucleophile. You would need a solvent in the reaction. And the reason why you need a solvent, because the alkene is water insoluble. Most of our reagents are water soluble. So to make these two miscible with each other, you would need a solvent. The reaction will proceed by breaking of the pi bond and forming of two sigma bonds. So you are adding the X and you are adding the Y. The solvent will not appear in the product. The solvent is just to dissolve the reactants and the reagents together. If you look at the alkene, alkenes are planar in geometry. And the hybridization of each one of these carbons is an sp2 hybridization. The carbon double bond carbon is nucleophilic. And the reason why it's nucleophilic, because you have a pi bond, which is the overlap of two p orbitals. So if we look at the valence bond representation of the pi bond, you would see that the electrons, they reside in the p orbital, and the p orbital overlap to make a pi bond for the alkene. So all of those are our sigma bonds, and you do have a pi bond in there. So this pi bond is going to make the alkene a nucleophile. Because the alkene is a nucleophile, meaning that it is an electron source. Because the alkene is a nucleophile, that alkene can react with any electrophile in the solution. This is why whenever you are doing the addition reaction, you would need an electrophilic site so that the alkene will come and react with. And always your arrow is going to start from the double bond towards the positive site. You are moving both electrons of the pi bond, so this is why you're going to use a full head arrow towards the partial positive atom. And then every time you make a bond, you are going to break a bond. So in this case, you're going to break a bond, and Y is going to be a leaving group that later on it's going to attack the adjacent carbon, and you're going to have an addition reaction. Let's go ahead and start with our first reaction here, which is called the hydrohalogenation. Now, hydrohalogenation is the reaction of alkenes with HX, and X can be either a chlorine, a bromine, or iodine. Not fluorine though, because we know that fluorine is a very bad leaving group because it's a strong base. All the other halogens here, they are good leaving groups, so the reaction can proceed easily. For example, if we have this alkene and we are reacting it with HBr, in presence of carbon tetrachloride. Carbon tetrachloride is an organic solvent that dissolves both HBr and the alkene. First of all, you have to locate your nucleophile. And your nucleophile, which is the source of electrons, is always the alkene. Second, you have to locate your electrophile. Your electrophile is a result of the direction of polarization, meaning that your electrophile has to be attached to an electronegative element. And the electronegative element here is going to be bromine. So bromine will pull electrons away from the hydrogen, and it's going to make the hydrogen partial positive. So here my hydrogen is going to be my electrophile, and my bromine is going to be the nucleophile. So definitely, nucleophiles are not going to react with nucleophiles. The nucleophile is going to react with the electrophile. So my arrow is going to start always from the double bond, and it's going to open up and pick the hydrogen and take this hydrogen. Now I am making a bond between the carbon and the hydrogen. So every time you make a bond, you need to break a bond. So now I'm going to end up having a leaving group in there, and the bromine is going to leave. This is how I represent my arrows, and this is called the mechanism of the reaction. Now, the question is, I have two carbons over here. I have a carbon here and I have a carbon there. And the addition is going to be along these two carbons. So I have nothing to do with these two carbons there. Where should the hydrogen go? Should it go on this hydrogen or on this hydrogen? There's a rule, and it's called Markov-Nikov rule. And Markov-Nikov rule says that always you want to form the most stable carbocation. Always. So to form the most stable carbocation, according to Markov-Nikov, hydrogen needs to add to the less substituted carbon. So hydrogen adds to the less substituted carbon, and the bromine is going to add to the most substituted carbon. Always you start your addition with the hydrogen in this case because your hydrogen is the electrophile. Always your addition starts with the electrophile. Hydrogen is the electrophile. So in order to make the most stable carbocation, your hydrogen needs to go to the less substituted carbon here so that your most substituted carbon is a plus charge, is a carbocation. So now I'm going to end up forming a positive charge here and a hydrogen over there. Okay, now after I do the hydrogen there, now my bromine is going to be in the solution. Now this Br minus is a nucleophile and it is in the solution. So this Br minus now it's going to come and it's going to attack the carbocation. But before attacking the carbocation, ask always, can I make it more stable? This one is a secondary carbocation. If you move it here, it's going to be a secondary. If you move it here, it's going to be a primary. So no, you cannot make it a more stable carbocation. So now you can proceed. This is a secondary carbocation. So to proceed in there, bromine is going to attack. If you look at the hybridization of this carbon over here, this is an sp2 hybridization. Don't forget that carbon, when it is positive charge, it has 3 bonds in there. So definitely you do have a hydrogen here. So here what you have is basically 1, 2, and 3 groups. This is a CH3, this is an ethyl, and this is a hydrogen. So this is the 3 different groups, and you're adding a bromine in there. So it's going to be 4 different groups. So you're going to create a chiral center in this case. The positive charge is a planar geometry. Planar means that the attack of the nucleophile is going to be on both sides. It's going to be on the right or on the left. So in this case, it's going to attack either to the top or it's going to attack at the back. So it's going to be either attacking in front or attacking at the back. And you always consider stereochemistry whenever there is a potential that you are forming a chiral center in this case. So bromine now, it's going to go ahead and attack from the top. And in this case, the hydrogen will be at the back. And don't forget, on this carbon, because this is where my double bond was, okay? I already added a hydrogen on this carbon. No need to show the hydrogen. It's already a CH3 in there. Plus, the bromine can attack at the back. And if bromine attacks at the back, then in this case, the hydrogen, it's going to be in front. So what you did over here, you created a chiral center. And these two are going to be enantiomers. So you get a pair of enantiomers in there. But because you are starting with an optically inactive reactant, then your products are going to be optically inactive, which is a racemic mixture in there. Let's have another example. So first, start locating your double bond and your electrophile. So hydrogen is going to be my electrophile in this case because the chlorine is the electronegative element. So my arrow is going to be from the nucleophile towards the hydrogen. Apply Markov-Nikov. Hydrogen always needs to be added to the less substituted carbon. So among those two carbons that I have here, I have a carbon here and I have a carbon here. This carbon is the less substituted one. And the reason why it's less substituted, because if you look at this carbon is connected to one carbon versus this carbon here is connected to two carbons. So it is the less substituted carbon. So hydrogen is going to add to the less substituted carbon so that the adjacent carbon will carry the positive charge. Again, these reactions, they proceed by carbocation formation. So hydrogen here is going to add to the less substituted carbon, and the chlorine is going to add to the most substituted carbon. But you have to keep in mind always that you have rearrangement, always. So over here, I am going to add my hydrogen first. So hydrogen is going to come and add over here, and the adjacent carbon will carry a plus charge. Now that adjacent carbon over here is already a tertiary carbocation by itself. So no need for me to move anything in this case because it is already a tertiary carbocation. So I can go ahead and proceed. So I'm going to go ahead and add my chlorine in this case. Every time you make a bond, you break a bond. So you have to show that the chlorine is leaving. And the chlorine now is going to be in the solution. So that the chlorine is going to come and is going to attack now the most stable carbocation, which is the tertiary carbocation. So the chlorine is going to come now. As we said before, the carbocation is planar in geometry. And because it's planar in geometry, the attack of the chlorine is going to be from both sides of the carbocation. So the attack of the chlorine is going to be from the front, and the attack is going to be from the back. So you are going to end up getting two isomers in this case, or two stereoisomers in this case. Here you go. So you're going to end up getting a chlorine that is in front plus. If the chlorine is in front, then in this case, the ethyl group is going to be at the back, plus, and you have here just one chiral center. The ethyl group is going to be in front, and the attack of the chlorine is at the back, and these two are going to be a pair of enantiomers, and they are going to be a racemic mixture. Let's have another example now with hydrogen iodide in presence of carbon tetrachloride. Same idea, locate your double bond in there. And the reaction goes from the nucleophile to the electrophile. So the double bond is going to open up, pick up the hydrogen, and the iodine is going to leave. Every time you make a bond, you break a bond. This is the mechanism of the reaction. And now my hydrogen will add to the less substituted carbon. So this carbon over here is going to be the less substituted carbon, and this carbon over here is going to be the most substituted. So this is going to be the less substituted, and this is the most substituted. And the reason why this is the most substituted is because this carbon is connected to a carbon with two carbons. This carbon is connected to a carbon with a carbon. So this is why this one is the most substituted. So I want my carbocation to be on this carbon. Now, the carbocation here is a secondary carbocation. And that secondary carbocation, I have a potential of rearranging it by making it a tertiary carbocation. So if I move this positive charge here, it's still going to be a secondary. But if I move the positive charge here, then it's going to be a tertiary. I can move the carbocation by simply doing a hydrogen shift. So you take the hydrogen together with its electrons and move it towards the carbocation, its electrons towards the plus charge. And when doing that, then we are going to end up having our positive charge on this carbon, and this is a tertiary carbocation. Now notice that this carbocation, it is planar, yes, but it doesn't have three different groups on it. So it's not a potential for a chiral center. So once I go ahead and use the iodine now, don't forget that you are not done yet. because iodine is still in the solution. This is I minus, it's still in the solution, and it's waiting until you form the most stable carbocation so that it comes and attack. So now the iodine is going to come and it's going to attack, and the iodine is going to attack from the top and from the bottom, but because you don't have any stereochemistry in here, this is not a potential of a chiral center, then you don't have to consider stereochemistry. Just allow the iodine to attack in this case, and you are going to end up just one product. You don't have to show stereochemistry, so iodine is going to be over here. And don't forget that you have your CH3 as well. So that is going to be a CH3. This is not a chiral center. So this carbon over here is not a chiral center because you do have two groups that are the same. So you don't even have to show any stereochemistry for this reaction other than the addition of the iodine. So in this case, you would have added the hydrogen over here and the iodine over here. So the moment I look at the reactant and I look at the product and I see that the iodine is not added between the carbons of the double bond, I would immediately know that there is a rearrangement in this case. Since the CH3 stayed in its place, then it is a hydrogen shift. There was a hydrogen shift. The carbocation was on that particular carbon because always the halogen is going to come where the most stable carbocation is. This is another example, and in this example, I'm going more into details of the stereochemistry of the addition of not just the chlorine, but the hydrogen as well. Now, in the other examples that I went over, I didn't go over the stereochemistry of the addition of the hydrogen. I neglected this, and this is how we're going to go. We're not going to show the stereochemistry of the addition of the hydrogen, but in this one, I just want to show you how the hydrogen really acts. So you're starting with your alkene, and your alkene is a planar in geometry. So in this case, when the double bond is going to open up and pick up a hydrogen, since it is planar, then the hydrogen is going to have two options to attack. The hydrogen is going to attack from the top and from the bottom. And it's going to be on any one of those carbons because both carbons are the same degree of substitution. So let's say, for example, if the hydrogen attacks this carbon here. Because this is planar, the hydrogen is going to add either at the back or it's going to add at the top in this case. If it adds at the back, then it's going to push the CH3 to the front. And if it adds to the front, then it's going to push the CH3 to the back. Now, after you form your carbocation, so the second carbon over here is going to be a carbocation. There will be no rearrangement because it is a tertiary. Then the Cl minus is going to attack. And here the Cl has two options. Either the Cl is going to attack from the top and bottom of this carbocation, so you're going to end up getting two products, or it's going to attack from top and bottom of this carbon, so you're going to end up getting two products in this case. If you look at A and B have this carbon over here being the same. The only difference is the second chiral center. So here you have two chiral centers. However, so you have two chiral centers. So the first chiral center, this chiral center over here is the same, but the second chiral center here, it's different. So the second chiral center here, it's different. So A and B are considered to be diastereoisomers. C and D also, they are considered to be diastereoisomers because they differ just in one chiral center. The other chiral center is exactly the same. However, B and C, they differ in both chiral centers. So these are enantiomers, and A and D, they are enantiomers. So in normal cases, we skip this step and we assume that hydrogen is just adding in plane. And we proceed with the addition of the chlorine, showing the stereochemistry of the addition of the chlorine. Another reaction that HX undergoes with alkene, which is different than Markovnikov, is anti-Markovnikov. Anti-Markovnikov is the opposite of Markovnikov, and the reaction conditions are completely different. So with Markovnikov, we used carbon tetrachloride as a solvent. Here, instead of the carbon tetrachloride, we're using a peroxide. So whenever you see a peroxide is an indication that I am doing an anti-Markovnikov. And with anti-Markovnikov, this is the opposite again of Markovnikov. Hydrogen is going to add to the most substituted carbon now. No carbocation intermediate. There is no carbocation intermediate. There is no stereochemistry in this case. It's just hydrogen adding to the most substituted carbon and the bromine adding to the least substituted carbon. The way that I know that I am having an anti-Markovnikov again is look and see you have a peroxide. So if I have a peroxide, then in this case, I need to locate my alkene. So this is going to be my alkene. This is going to be my less substituted carbon. And this is going to be my most substituted carbon. So I'm going to start by adding the hydrogen to the most substituted carbon. Ignore stereochemistry. There is no stereochemistry. Just add them like that. And then a bromine will be added to the less substituted carbon. There will be no carbocation rearrangement. So no carbocation. And there will be no carbocation rearrangement. This reaction happens only with HBr. It doesn't happen with HCl and it doesn't happen with HI. There are additional examples on hydrohalogenation in the practice problems. Please practice those.